When I say the word ultrasound, what's the first thing that pops into your head? For most of us, it's that grainy black and white picture of a baby on a screen, right? That amazing first glimpse of a new life. And yeah, that's its most famous job. But believe me, it is just the very tip of the iceberg for a technology that has completely revolutionized medicine.
Just think about that for a second. I mean, we've got X-rays and CT scans, but they use radiation. We have MRIs, which use these incredibly powerful magnets, but what if there was another way? A way to get a live, moving picture from inside our own bodies without any of that?
The answer is sound. That's it. It's so simple it's almost hard to believe. We can literally see inside ourselves using nothing more than sound waves. Waves that are pitched so incredibly high, there's no way we could ever hear them. So, how on earth does this invisible sound create a visible picture? Let's dive in.
Okay, to really understand how this magic trick works, we have to get to know the tool itself. We are literally talking about using sound as a form of sight.
So, the core idea is actually super elegant. A machine sends these high-frequency sound waves into the body, then it just listens for the echoes that bounce back, and it uses that information to build a picture. You can think of it like a bat using sonar to navigate in the dark, but for looking at your own kidneys.
So when we say high frequency, just how high are we talking? Well, human hearing, for most of us, taps out at around 20,000 hertz. Medical ultrasound uses frequencies that are hundreds, sometimes even thousands of times higher than that. We're in the millions of hertz range, completely beyond anything we could ever perceive.
All right, so we're using silent sound waves to see. Very cool. But how does a machine actually turn those invisible echoes into a clear image on a screen? Let's break down the nuts and bolts.
It's basically a three-step dance. First, the probe, that handheld thing they put on your skin, it's also called a transducer, sends a really quick pulse of sound into the body. Second, that sound travels along until, bam, it hits something, like the wall of your liver or a blood vessel, and an echo bounces right back. And third, this is the brilliant part. The computer calculates exactly how long each echo took to come back and how strong it was, and it uses all that data to build the image pixel by pixel.
To make this a little more concrete, imagine the ultrasound screen is a giant blank spreadsheet. The machine sends a pulse of sound down, say, column A. If an echo comes back really fast, it puts a bright dot in a cell near the top, like A2. If another echo from deeper down comes back a little later, it puts a dimmer dot in a cell further down, maybe A15. Now, just imagine it doing that for every single column, thousands of times every second. And that's how you get a complete, moving picture.
But hang on, how does the machine know how deep something is? Well, it relies on one really simple and really crucial assumption, that sound travels through the soft tissue in our bodies at a constant speed of 1540 meters per second. Because it knows this speed, it can convert the echo's travel time directly into distance, letting it place every structure in the image with amazing accuracy.
And this is where we get to move way beyond just looking at babies. Because this technology is so safe, relatively cheap, and portable, it has become one of the most versatile tools in any doctor's toolkit. Let's look at just a few of its surprising uses. This quote really highlights a critical evolution for this technology. See, ultrasound isn't just for looking anymore, it's for doing. It basically gives doctors a live roadmap so they can guide a needle for a biopsy or drain fluid with incredible precision, all without having to do major surgery.
In the emergency room after a car crash, they can do something called a FAST exam. That stands for Focused Assessment with Sonography for Trauma, and instantly know if there's internal bleeding. Anesthesiologists use it to guide needles for nerve blocks, making procedures way safer. And cardiologists can watch your heart's chambers and valves beating in real time to diagnose problems right on the spot.
And the list just goes on. It can even be used to check the lungs, which is normally tough for sound because they're full of air, to spot fluid buildup or a collapse. It can find kidney stones or even produce a super detailed image of all the delicate little structures inside your eye. It is truly a go-anywhere medical tool.
But, like any technology, ultrasound has its superpowers and its kryptonite. And understanding both is really key to seeing why it's used so widely, but also where other tools have to step in.
So, on the plus side, it's live, it's portable, it's pretty low cost, and it is incredibly safe. There are zero known long-term side effects from it. But it definitely has weaknesses.
Sound just doesn't travel well through bone or gas, which is why you can't get a clear picture of an adult brain through the skull or see organs that are hidden behind the bowel. And maybe the biggest one, the quality of the image is hugely dependent on the skill of the person holding the probe.
So what's the big takeaway from all this? The real power of ultrasound isn't that it's the absolute best at every single thing. Its power is that it is safe, accessible, and dynamic. It brings the power of medical imaging out of the big radiology department and puts it directly at the patient's bedside, empowering doctors to make faster, more informed decisions right then and there. From its very first use, watching a heartbeat, to its future in things like molecular imaging, ultrasound is a technology that is just constantly evolving. It started by showing us the very beginning of a life. The question now is, as it gets more and more powerful, what other secrets will it help us see inside ourselves?